In this video, we will look at calculating shortest paths within networks. A path in a network connects two nodes. In the example, let's assume that A is the source and F is the target. There are multiple paths from A to F. Some paths will be longer than others. The highlighted path travels from A to F via nodes B and D. The path can be represented in two ways, as a sequence of edges, or as a sequence of nodes. The shortest path analysis finds the path that minimizes the sum of the edge weights. In the diagram, the edges now have a set of edge weights indicated. Notice that the edge weights may be different to the edge lengths. The shortest path from A to F turns out to go via node C, E, and D. The total path costs come to 20. If we assume that the edges are undirected, then the shortest path is reversible. This means that the shortest path from A to F is also the shortest path from F to A. Next, let's take a look at analyzing multiple shortest paths at the same time. Shortest paths can be calculated between multiple sources and multiple targets. The diagram shows one source with multiple targets in an undirected network. As an example, the source might be a transport node, and the targets could be destinations. The same result could have been achieved in reverse, with multiple sources and one target. In such a case, the analysis will generate multiple shortest paths. Many of those paths will have nodes and edges in common. This means that each node and each edge in the network is part of 0 or more paths. In the diagram, the edges in the network have been extruded based on the counts. Edges with higher extrusions are shared by more paths. The analysis can calculate the node count and edge counts. These metrics may be significant, depending on the type of network analysis being conducted. For example, if the paths represent pedestrian routes, then the counts may be indicative of the number of people traveling through each node or along each edge. Note that the node counting approach is similar to between the centrality, which will be covered in a later video. Another common use case for multiple shortest paths is finding the closest node in a network, given a set of targets. For example, the targets may be a set of transport nodes. The analysis can then find the closest transport nodes for various points in the network. This types of analysis consist of two steps. The first step calculates the shortest path from each source to all targets. The second step then selects the closest target. In the diagram, the network consists of a grid. The four corner nodes are defined as targets. For each node in the network, the closest target is then calculated. The extruded height represents the number of closest paths traveling along each edge.